So I just want to start by thanking Mohammed for again putting on a fantastic meeting. It's great to be back here face to face in Oxford for the first time for a couple of years. For those of you that know me, I'm used to walking around the stage, so this is going to be torture for me for the next 30 minutes being stuck here at the podium, but I'll see what I can do. For those of you that don't know what my lab does, we're interested in using arthropod venoms as a source of peptide drug leads for disorders in which ion channels play a really important role in the etiology of that disease. And that probably raises two questions in your mind: why arthropod venoms and why diseases in which ion channels are involved? And the reason is that 99% of all the venomous taxa on the planet are invertebrates, and of those, more than 90% are arthropods. So they represent by far the largest number of venomous taxa on the planet. They're also full of these small disulfide restrained peptides that make them really ideal therapeutic candidates. And the other thing is that they're the richest source of ion channel modulators. And why is that important? It's because ion channels are incredibly important therapeutic targets. We think of GPCRs as being a really important class of human therapeutic targets. But after GPCRs, which you can see over here for small molecule drugs, is the largest class, ion channels are the second largest class of small molecule drugs, and they're actually the largest class of biologic drug targets. So, and they're incredibly important class of ion channel of drugs. And in fact, many of them are very hard to drug, except with the sort of complex peptides we find in venoms, and arthropods, as I said, are the richest source of those venoms. So the disorder I want to talk about today is the greatest cause of mortality in the world, which is cardiovascular disease. It's both the greatest source of mortality and it's the greatest socioeconomic burden. So about 18 million deaths a year, about 30% of all deaths every year are due to cardiovascular disease. And of those, most deaths are due to the acute manifestations of CVD, which is stroke and heart attack. So about 15 million deaths a year combined. The socioeconomic burden is enormous. By 2035, the cost in terms of direct medical costs and lost productivity is going to be over $1 trillion a year. And the reason that they cause so much, but let me just say something. I mean, when I say 15 million deaths a year, to me that it's hard to absorb what that number means. And so I want to try and bring that home to you. So during the course of this talk, this 30-minute talk, about 350 people are going to die from a stroke. A similar number of people are going to have a stroke, survive, but have a permanent disability. That's just within the next half an hour. And during the same period of time, about over 500 people will die from a myocardial infarction. Many thousands more will survive their heart attack, but many of those will go on to get heart failure and they'll ultimately need a heart transplant. So the burden is enormous. And the reason it's so high is we have no drugs to treat either of those diseases, not a single one. It's a singular failure of modern medicine that we have no drugs to prevent the tissue damage that occurs during a heart attack or stroke. And that's why the burden is so high. And that's why there's this huge unmet medical need for neuroprotective and cardioprotective drugs that we can use during these acute manifestations of cardiovascular disease. And that's where I'm going to introduce you to this ion channel, which we think may be the solution. So there's a really unusual class of ion channels known as acid-sensing ion channels, or just ASICs. They're proton-gated channels. In other words, the ligands for these channels are just hydrogen ions. They're expressed primarily, but not exclusively, as I'll show you, in the peripheral and central nervous system. There are 4 genes, 2 of which get alternatively spliced. So there's 6 subtypes, and they form homo or heteromeric channels that have different channel biophysics, different pharmacology. This is what the channel looks like. So it's trimeric channel, as I said. The 3 subunits here are colored differently. And if I do a surface representation and map on the charge, you'll see there's a deep acidic pocket. And that pocket is where both the ligands, the protons, bind to activate the channel, but also where all the ligands I'm going to talk about actually bind to the channel. These channels for some time were known to be involved in pain sensing. But there's a subtype called ASIC3 that's in the sensory afferents that innervate the heart, for example, that's involved in angina pain. And the subtype I want to talk about, ASIC1A, was initially thought to be involved in pain. That turned out to be a mistake. It was the splice subtype, ASIC1B, that's involved in pain. But nonetheless, it's a very interesting channel. It's the most pH sensitive channel. It starts to activate when the pH gets to 7. And it's about half activated at pH 6.6. And it's the only one of the ASIC channels that will carry calcium in addition to sodium. And that's important for what I'm going to talk about today. This is the paper that got me really excited about this channel in the context of stroke in particular. So it's a very old paper, 2004. I didn't discover it until about 10 years later. What they did was knocked out this channel ASIC 1A and gave a stroke to these knockout mice or naive mice. And what you can see in this graph on the right here is the infarct size, that's the amount of brain tissue that's effectively lost in the stroke, is diminished by 60% in the heterozygous knockout mice, which otherwise are phenotypically normal. So the simple act of knocking out this channel reduced the severity of the stroke by 60%. And I thought that was absolutely incredible. And the question was, could we recapitulate that pharmacologically? I guess the question you're asking, though, is why is this proton sensing channel involved in the damage that you see during a stroke? And it's all to do with the biochemical changes that happen during a stroke. So in a stroke, there's a blocked cerebral artery. So there's a lack of blood supply to that part of the brain. That brain's not getting as much oxygen as normal. And so it can't burn its fuel in the normal way. The brain uses about half of all the glucose that we consume. Neurons are very energy hungry. It can't burn glucose anymore oxidatively. It has to resort to anaerobic glycolysis. And as most of the biochemists in the audience will know, the end product of glycolysis is lactate. So this is the same thing that happens when you're working hard in the gym. You just can't get oxygen to your muscles fast enough. You revert to this anaerobic glycolysis. You build up lactate. That's what gives you that burning sensation after exercise, but you can clear that fairly quickly, right? The brain can't do that now because it's got a blocked artery. So the lactate keeps building up and the pH goes down. And so in the most affected part of the brain, the pH can get to as low as pH 6. And I said to you, this channel starts to activate when the pH gets below 7. So it's very robustly activated in the context of a stroke. And what that does is two things. It carries calcium into the cell. It also depolarizes the neuron, which brings in more calcium via voltage-gated calcium channels. So it increases the calcium overload you see in neurons after a stroke. But remarkably, this channel actually recruits one of the master regulators of necroptosis and activates that kinase. It's called RIP1 kinase. So it activates that kinase and sets off a cell death pathway. So what's happening is in the context of stroke, this channel gets activated and it sends a signal to the neuron to commit suicide. So we think a lot of the neuronal death that we see in a stroke is due to this channel being activated. And what we asked is, could we come up with a pharmacological inhibitor of this channel that still worked at low pH? And would that prevent all the downstream effects that we see from activating the channel? And we got really lucky. This was a really serendipitous event. And for the students in the audience, there's a message here to be aware of what's happening around you. So I had a really talented PhD student in lab, Sani Pineda from Guatemala, who was simply working on the evolution of the venom of the Australian funnel-web spider. And the reason she's doing that, it's one of the most complex chemical arsenals in the entire natural world. It has over 3,000 peptides in the venom. And in the process of that, she recognized a molecule that was similar to another spider venom peptide that was inhibitor of the channel and we'd shown had benefit in an ischemic stroke. But she wasn't working on the stroke project, but she was well aware of what was happening around her. And she came to me and said, I found this molecule that looks really interesting. And this was the molecule. And it was interesting, but it was also shockingly large. It was 75 residues and it had 6 disulfide bonds, which means there were 10,395 possible disulfide isomers. But it had all the residues that we knew from this other peptide were important for engaging with the channel. So we thought it would indeed be very interesting to make this molecule. And fortunately, we had another very talented undergraduate at the time, French undergraduate, Irene Chazignon, who decided to have a crack at making this. So she was able to actually make this in E. coli. She was actually able to isotopically label the protein so we could do the NMR structure. And this is what it looks like. It's a rather large molecule, but you can see it's composed of 2 very similar domains. In fact, this toxin evolved via gene duplication of what we know as a Norton domain. So you can see each of those domains has 3 disulfide bonds. And those disulfide bonds form a very particular arrangement, which is known as an inhibitor cysteine knot or a Norton domain. And so for those of you that don't know what that is, I'm going to show you why it's such a cool domain from a therapeutic perspective. In each of those domains, if we take the top disulfide and the bottom disulfide and the intervening sections of the polypeptide backbone, it forms a closed loop. And the third disulfide here, which I've shown in orange, dies through the center of the loop, which you can see better in the animation. So this third disulfide actually dies through the center of the loop and basically ties the polypeptide chain in a knot. And what that does is give these toxins incredible resistance to proteases. And so if we take this peptide and put it in human plasma over a period of 5 days, not 5 hours, 5 days, we see hardly any degradation at all. It's super, super stable. And that's common with these notons. This is not an unusual, atypical example. That's pretty common. So the question is, did it inhibit the channel as Sandy had predicted? And the answer is yes. And it turned out to be by far the most potent inhibitor of this channel that anybody had ever discovered. So that was a wonderful serendipitous discovery by Sandy. It inhibits the channel with an IC50 of about 500 picomolar. We think it's actually lower than that now. To give you some context, it's about 50,000-fold more potent than the best known small molecule inhibitor of the channel, which is the antidiuretic trigamiloride. The other thing we really liked about it is the other peptide we had been working on was this green one, PCTX1. It's a good inhibitor of the channel, not as potent as this one called HO1A. When we try and wash it off the channel, which is what this green line is showing, we recover the currents relatively quickly, so it washes off fast. But when we try and wash this peptide off, HO1A, it's very, very slow, and that fits in with the fact that when we measure its affinity using surface plasmon resonance, the KD is less than 50 picomolar. So it's a super tight binder. Its PK is not great, but if you inject it IV, you can see it on the heart. I'll talk about in a minute, 5 hours later. The mechanism is interesting as well. So this channel is unusual in that it goes through 3 states. From the resting state, it's opened by protons, then it rapidly desensitizes, and it takes a long time to recover from desensitization. These experiments are single channel experiments of the type that I think Jan is probably very familiar with. And so this is where you take small patches of the cell that are expressing the channel. So you're only looking at one channel at a time. So the currents are very tiny. You can see it's about 2 picoamps. So what you see here is when you drop the pH from 7.4 to pH 6, the channel turns on. So this small blip, downward blip, is the current from a single channel. But you can see it turns on straight away. But in the presence of the peptide, there's a huge delay before the channel turns on. In other words, what this peptide is doing is inhibiting the activation of the channel. And that was really important for the mechanism because remember, as soon as this channel activates, it recruits that mediator of necroptosis. So this was the exact mechanism that we wanted. So we're excited by that. I don't want to go through this because this was published a long time ago and I presented this last time I was here, but when we gave this molecule at a very tiny dose, almost homeopathic, 2 nanograms per kilogram ICV, either 2, 4, or 8 hours after a stroke, we saw a 60 to 80% reduction in the size of the brain damage. It was an extraordinary result. And there was a concomitant improvement in the neurophysiological behavior of the animals. So it was a really exciting outcome. And we think this molecule has huge potential for stroke. But I'm not going to talk about that because I talked about it last time. What we thought that was, given that this channel seemed to be so important in this ischemic injury of the brain, the question was it important in ischemic injury of other organs? And if you look at how long you can keep an organ after you take it out of a donor before you have to transplant it, you see that the heart is the organ that's most susceptible to lack of oxygen. So you can keep a kidney for 2 days. You can't keep a heart for more than 3 or 4 hours. In other words, if you have a donor in Los Angeles, you're not going to get that to a recipient in New York. The heart is not going to last long enough. So the question is this channel important for the heart, and can we use it to protect the heart from ischemic injury? And again, this is where, again, something very serendipitous happened. Just as we had finished the stroke study and had just completed publishing it, we had a new group leader arrive at our institute. Nathan Palpan had just arrived from Seattle, and luckily for me, he was a cardiac physiologist. And I said to Nathan, what's known about this channel in the human heart? And he said, nobody's even looked. We don't know if it's there. So we set out to try and find out whether the channel was there. We got some data, some RNA-seq data from another lab looking at mouse cardiomyocytes. We saw that it was there both in young mice and old mice. Expression wasn't changed by myocardial infarction. What Nathan can do is make it induce pluripotent stem cell-derived human cardiomyocytes. And so we're able to look in human cardiomyocytes and see if it was there. And it was in the human cardiomyocytes. The level doesn't look to be very high, but I just want to point out this last one marker that we compared it against is the voltage-gated channel NaV1.5, which is the generator of cardiac action potentials. Really, really important channel for the heart. And it's expressed at a higher level than NaV1.5. So we think it's still reasonable expression. So we saw it was there, and the question is it important for ischemic injuries to the heart? And for that, we first of all used this ex vivo model of cardiac ischemia reperfusion injury called the Langendorf perfusion model. It's a really cool system. You can take the heart out of usually a rodent or even a pig, and you retrogradely perfuse it through the aorta to keep it going. And you can actually keep the heart alive for several hours. So for those of you that have never seen it, this is actually a rat heart on a Langendorf rig, beating at a couple of hundred beats per minute. And you can keep it going like this for several hours. But because you're controlling the perfusion of the heart, you can stop that and effectively give it a heart attack as though it had a blockage in an artery. And that's exactly what we did. So the first experiment we did, though, was we did it with normal mice and a mice with a knockout of that channel. And asked the question, do the knockout mice recover better? In other words, is that channel important for the ischemic injury of the heart? And this is the experiment here. So we're measuring left ventricular developed pressure, and we're going to turn off the perfusion for 25 minutes. So you can see the pressure plummets to zero and remains that way until 25 minutes when we turn the perfusion back on. Then something really interesting happens that I want to explain to you, and that is the pressure recovers quickly, but then it precipitously drops again. And that's the paradoxical reperfusion injury. So in a myocardial infarction, a heart attack, obviously you have to reperfuse the organ or the person will die. You need to get oxygen back to the heart. But paradoxically, the act of reperfusion itself causes additional injury. So this is the reperfusion part of the injury. And then you can see the heart slowly recovers. So this is the wild type mouse. You can see the mouse with the knockout of the channel recovered better, which suggests that that channel is actually important for ischemic injury of the heart. So then we went ahead to see if we could recapitulate that pharmacologically, and you can see with just 10 nanomolar of this peptide in the perfusate, we get a much better recovery of the heart after this ischemic event. And we measured a whole bunch of different parameters, and they all reflect the same result, is that the cardiac performance is much improved in the presence of the peptide. So then we went to an in vivo model of myocardial infarction. So this is where we ligate the left anterior descending artery to mimic a blockage in that artery, one of the major arteries leading to the heart. And so the ligation was for 40 minutes. So it's a fairly serious injury. And we delivered the drug either before we did the ligation, just after the ligation, or just prior to when we reperfused the heart. Now, probably most of those interventions make sense, except the first one. You might ask, why on earth would you be interested in whether the drug would work before the injury starts? Because you don't know when you're going to have a heart attack. And that's entirely true, but you do know when you're going to do coronary surgery. So for example, coronary artery bypass surgery is a fairly common surgery. By definition, you are going to bypass the heart. It is going to get an ischemic injury. So in that case, you might want to give the drug before the surgery. Or for example, if you're doing an aortic valve replacement, you might want to have some drug on board. The second scenario there would be equivalent to a first responder giving the drug soon after the person began having the heart attack. The final intervention is more what would happen in the hospital. You give the drug just prior or at the same time you're trying to give the person an angioplasty and put a stent in to open the artery back up. So we delivered the drug 1 milligram per kilogram IV, and you can see under all those scenarios, which are the first three here, we get about a 40 to 50% reduction in the infarct size. So this is a measure of the infarct size. If we go to 0.5 milligram per kg, just prior to reperfusion, we still get a really good effect, but we lose it at 0.1. So there's some nice dose dependence going on there. What's perhaps most important is the graph on the right here. So this one here, this is measuring something called the ejection fraction. It's a really good measure of the performance of the heart. What I should have said is that these mice, we did an echocardiogram before the surgery, and then we did an echocardiogram at 7 days and 28 days. So these are the results of the echocardiograms looking at this thing called ejection fraction. So the ejection fraction, as it says there, is the percentage of blood the left ventricle pumps out with each contraction. If that gets below 40%, it's a good chance that person's going to develop heart failure and ultimately need a heart transplant. So you can see in this experiment, it gets down to close to 40%. In the vehicle-treated animals, then slowly recovers. But this is what's really cool is the animals that got the drug had a really good maintenance of that ejection fraction. Now, what's exciting is that was a similar performance to the only drug that has ever worked in clinical trials as a cardioprotectant. It's a drug called cariparide. The clinical trials were done around the turn of the century. It's an inhibitor of the sodium proton exchanger, and it gave a similar increase in ejection fraction in human patients in a phase 3 clinical trial with patients that had a STEMI heart attack, which I'll explain in a minute. This would have been a drug that would be used today for heart attack to help people recover, except for one problem. It had cerebrovascular side effects. Some people got a stroke. So its clinical development was dropped at that point. We know that won't be a problem with our drug because it actually is beneficial for stroke. So we're hoping that this has all the good effects of cariparide, but none of the downside. And that's just summarizing the different scenarios. So we could give this, we think, first by first responders or in a hospital setting. I just want to show you this because I think I'm still blown away by this experiment. This is probably the most profound ischemic injury that the heart can ever suffer. And it's when hearts are donated by a procedure called donation after circulatory death. So most donor hearts come from brain dead patients. But there is another potential way to get donor hearts, and that's people that have just been taken off life support. So they're taken off life support. The definition of death in that case is asystole, so the loss of ventricular contractions. And as Wikipedia says, which is the source of all scientific knowledge, asystole is the most serious form of cardiac arrest and is usually irreversible. And so it was always thought you could never recover these hearts. But Peter McDonald, the cardiac surgeon we work with, one of the best heart transplant surgeons in the world, has shown that it is possible if you take those hearts, put them on one of those Langendorf type rigs that I showed you and perfuse them. You can get them going again. But let me show you the problem. So this is an attempt to simulate that type of donation in a pig heart. So you can see on the left, the pig there, the first heart is just after withdrawal of life support, which is simulated in this experiment by tracheal ligation. So life support's turned off. You can see the heart gradually progressing to asystole. And one of the problems with that in a real life situation is that's a variable progression in a human patient. Now, and you can see at the end of asystole, the heart has stopped beating. And I think this microphone may have also stopped working. Sorry? Okay, I'll try and talk louder. But the situation is even worse than that because all jurisdictions around the world say that after the heart has stopped beating, you have to wait a standoff period to make sure it doesn't restart. In Australia, that is 2 minutes. So you've now got a heart that's dead, still sitting at 37 degrees. You can't open the patient up and you've got to sit there and wait. It's incredibly frustrating, right? But Peter has shown that if you can get this all done, if you can get this done in about 15 minutes, then those hearts are recoverable. If it's any longer than that, they discard the heart because you're not ever going to be able to recover it. So the experiment I'm going to show you is that same sort of experiment that I showed you with the pig hearts, but now we've left 20 minutes of warm ischemic time. And in this scenario, Peter has never, ever been able to recover a pig heart. And that's shown here. So this is the sham animals in black. And down here are the animals that either received vehicle or vehicle plus heparin or vehicle plus heparin plus tyrofibam, which is anticoagulant and antiplatelet. And as you can see, once you place some arterial pressure on these hearts, they just die. They just can't respond. But remarkably, and even though this is N equals 3, the green line is what happens again when you put 10 nanomole of this peptide in the perfusate. These hearts miraculously recover to almost the same capacity as the sham hearts. It's like they were never damaged at all. They never suffered this warm ischemic time. So this is by far the most profound result we've ever seen, and we think this peptide really is going to be helpful in the context of heart transplant in terms of being able to get more hearts into patients, but also get better quality hearts into patients. So just to finish off, we've shown now that this peptide works in rodent and pig models of various diseases, including ischemic stroke, heart attack. I haven't shown you the data, but it works in kidney ischemic reperfusion injury. Another group has shown it works in multiple sclerosis. It doesn't work for everything. We're about to publish a paper that shows knockout and pharmacological inhibition of the channel does nothing in terms of recovery after spinal cord injury. And so on the basis of that, we were able to go out and raise some money to start a company to try and take this into clinical trials. So that company is called Infinza Bioscience, and that's where I spend about 75% of my time at the moment. And the plan is to take this initially into clinical trials for a type of heart attack called STEMI heart attacks, or ST segment elevation myocardial infarction. This is something that can be easily diagnosed in an ambulance with an ECG. So this is a typical ECG. This is the ST segment here. And in a STEMI heart attack, you see a big elevation of that ST segment. So it's easily diagnosed. The paramedic knows automatically that is a very, very serious heart attack. And the standard of care around the world is to get that person to hospital within 1 hour so they can have what's called percutaneous coronary intervention. So they'll go to a stent lab where they'll get an angioplasty and a stent inserted at the same time. The reason we like this group as the first clinical trial is it's a fairly homogeneous group in terms of their type of heart attack, in terms of their type of treatment, and because it's very severe, we think we have most chance of showing an effect. So the aim is to try and get this into phase 1 clinical trials, which is just a safety trial, towards the end of next year, and then towards the end of the following year to get it into clinical trials in STEMI patients. So hopefully I've convinced you that arthropod venoms are a really good source of ion channel modulators, that many of these are disulfide-rich peptides, which can have extreme protease resistance, which is good for the use as therapeutics, but they also can have exquisite potency and selectivity, which are also great properties. And hopefully I've convinced you that this is a promising drug candidate for treatment of heart attack and stroke. I think I've mentioned most of the people all the way through. I want to pay particular thanks though to Nathan, Meredith, a postdoc in his lab, Peter McDonald and Sarah Shewer, who did all the brilliant heart transplant work, and particularly to Natalie Sayez in my lab, who's been the champion that's been making this peptide for the last 5 years, and that's fueled a whole range of experiments in lots of different laboratories. So she's done an amazing job. I want to remind you that the 21st World Congress is on in Abu Dhabi in October. If you can't go, it's virtual, so you can register. And you probably haven't heard about this though. So those of you who are interested in the sort of things that some of us have talked about in this session, the 8th installation of the Venoms to Drugs meeting is happening in Australia next year. For those of you who don't know, the modus operandi here is we always have it on an exotic island. And this occasion will be on Moreton Island. It's a famous island because you can go and feed the dolphins. It's quite near Brisbane. It's a very broad church. We talk about drugs, insecticides, antivenoms, everything. So if you're interested, come along. And with that, thank you for your attention. I'll be happy to answer any questions. Short answers, okay. I'm on notice.
Thank you. That was fascinating.
Thanks, man.
How does your work relate to work such as that being done at Yale, like by Organ X and these other resuscitative companies? And do you see a collaborative
I mean, the guys that are making the perfusion machines?
Mm-hmm.
Yeah,
So that would be a good synergy there.
Absolutely, you know, quite right, Matt. So yeah, the recovery of those DCD hearts requires them to be put on a rig. That rig's actually quite expensive. It's between $25,000 and $50,000, and it's one-off use. So if you don't recover the heart, you've lost 25 to 50 grand. So, but if you can use the peptide along with the machine, your chances of recovering the heart are significantly improved. And So one of them's already reached out to us, Matt, about potentially including it in their perfusate solution. And I agree, it's a definite synergy there. Great question.
Comments, questions?
So at the beginning, you had mentioned, you were talking about the neurons, and I think you said that the channels open up when the pH is below 7.
Correct.
Okay. So in patients who have status epilepticus, prolonged seizures, they
Yes.
tend to build up extremely high levels of lactate. So, and in a lot of those cases, unfortunately, there's neuronal damage after that.
Yes.
So is this something that might be beneficial for
Yeah, no,
a status patient?
It's a great question. Epilepsy is one of our other interests as well. There's conflicting data. There's some evidence that this has actually evolved in termination of seizures, ASIC1A, but that data is conflicting. And the reason we got hold of that knockout mouse is that Steve Petrie, who you may know, is big in the epilepsy field, wanted to test that by making ASIC1A knockout and looking at some epilepsy models. And I don't think he has that data yet, so I don't know. But we'd love to look at that more and talk to you about it, because that's a big interest of ours as well. Thanks again. That's one over there.
Cheers, thank you very much. Hi, Glenn. Thank you so much for speaking. This is absolutely superb work, and really lovely to hear so many talks today that have actually been a little, dare I say it, optimistic about what we can do with Venoms. Just really, I think going all the way back to your introduction, any idea why funnel web spiders have this really incredible, massive peptides inside their venom, and you have these really unique ones like the one you were using for the drug? Is it an overkill strategy by the animal, or is it just...
It's a great question. That's why Sandy was doing that work, to try and understand how that venom evolved to be so complex. And I don't think we still have a good answer. I think it's partly overkill. Spiders, unlike many snakes, are generalist predators. This particular spider will take anything. It lives in a burrow, comes up at night, sits on the edge with a couple of tripwires. Anything that goes past, it'll jump on. So it could be a beetle, it could be a caterpillar, it could even be a small vertebrate. So it has to have a plethora of different toxins that will capture any taxa that it happens to jump on. But nonetheless, 3,000 seems like gross overkill, and we really don't understand why it makes so many. It's a great question. Great for us from a therapeutic perspective, because we're really interested in these things as basically mini drug libraries. And so we have a collection of over 500 venoms, and if you argue each of them has a couple of hundred toxins, then we can screen those venoms, and we're screening hundreds of thousands of compounds at once.
Great. Thank you very much.
You're welcome.
Sorry, I've hijacked it. I've got one question. Sorry,
Sure.
just from a more clinical angle.
Yes.
I presume in the context where you have someone who presents with a STEMI, but the pathology underlying is different. So in the instance of cocaine use, if you have coronary vasospasm, or in Takasubo's cardiomyopathy, my assumption is this would not work, but is that correct?
Oh, it's a good question. I mean, it's going to work for well, not any, but it's basically what it's going to work in is any ischemic event. So if that's causing an ischemic injury of the heart, then there's a chance that it would have some effect, but otherwise probably not. Because the channel's not going to be activated unless the pH is dropping.
Because I guess you want to try and dilate those vessels to try and, rather than...
Yeah, this has no effect on the vascular. So this has got nothing to do with dilation of the vasculature at all. Yeah. It's to do with setting off the train of biochemical events that's going to cause either the cardiomyocytes or the neurons to die. You still need to reperfuse, right? If you don't reperfuse, then you might have a good looking heart, but you're still going to die. Right? So you still need to reperfuse.
No more question for our multitasking speaker.
I have a question, if I could ask. Sorry.
Oh.
I'm Pradeep from Reading. So nice talk, Professor King. I just wanted to ask regarding this antipod venoms in general, like since you worked on it quite a bit, like would significant pH changes affect the natural structure and thereby the function of it in the crude venom if we were to use that in experiments? Do you think?
So I'm not quite sure what the question was.
Would significant pH changes affect the structure or function of a venom toxin in its natural state?
Yes, yeah, that's a good question. No, certainly not acidic pH. So these things are super stable in very low pH. The only time they become unstable is if you get above pH 8, because then you start to reduce the disulfide bonds, or at least you can get disulfide bond shuffling, because the pKa of cysteine is about 8.3. So they don't like alkaline pH, but they very happy at acidic pHs, which is the conditions under which we want to use them.
Okay, even when we are interacting with blood or platelets, which are like blood
Yep.
is at 7,
Yeah.
so that should be fine, right? So,
Yeah, no,
okay.
they're super stable under those conditions, and that's
Okay.
why we like this class of molecules.
Okay. Thank you very much.
You're welcome.